Let's look at the modeling on spread premix frames introduced by Williams in 1985 in the book of F. Williams. And as I described earlier, we consider the spread frame structures like the plot shown in the page of 3.34. Here, they describe there is the premixture of gasified oxygen and fuel vapor with the fuel droplets. In these mixtures, actually, they assume oxidizer is easier to be evaporated as a gas, right? Therefore, from the beginning, they assume oxygen already provide because the easier gasification from the injector and also the gasification process in the upstream sites. And that means that we just look at the influence coming from the liquid droplets, okay? This mixtures contains the gaseous oxygen and some fuel vapor evaporate earlier in the beginning and also have some liquid droplets, okay? Now, as I described, when this two-phase flow, two-phase mixture flow continuously from the left-hand side to the right-hand side, and since we already have some fuel vapor mixed with oxygens, that means that in gas phase, actually, you already have some mixing of fuel vapor and oxygen. They will give you a possibility to generate a bulk premix frame. Actually, this is controlled by the gas phase of oxygen and fuel vapor. Okay, and here you can see that there's a region to let you know there is a homogeneous combustion exists. It's just like a frame sheet of your premix frame. Okay, now in the premixtures, you still have a certain amount of liquid fuel, right? And those liquid fuel initially in the upstream side, maybe the temperature is not is does not high enough because you see the frame the temperature profile of premix frame in the upstream side. Actually, temperature is quite low, but when the flow moving closer to the premix frame front, then the temperature will be increased, which means they will go to the preheating zone. Inside of the preheating zone, the temperature is gradually higher when they're approaching to the flame positions. Then they will they will reach to the highest temperature. That means the flame temperature. Okay, in this region, definitely you will think about the liquid droplets passing through this preheating zone. They will go through the strong gasification process because the environment temperature is continuously increased. Okay, now the criterion is, do we have individual droplet burning after the premix frame or inside the premix frame? Yeah, this the definition or the determination on this criterion basically is coming from the uh, do we have a limit for the evaporation for the droplets? Definitely, if you have a very tiny droplets, then they will easily to be gasified in the preheating zone. Then when the flow flow into the bulk premix frames, actually they do not have a chance to have a liquid drop, right? But if you have a large droplet, then the droplet lifetime is longer. Then you may have a droplet itself as a liquid inside of the premix frame. Then you may have the so-called the heterogeneous burning because in the gas frames, gaseous frames, you will have a tiny droplet burning inside of the reaction zone. Okay. Now the criterion for the distinguish between the homogeneous burning and the heterogeneous burning depend on the traveling of your droplets in the preheating zone. In this traveling process, the droplet can complete evaporation or not. Okay. Now let's look at the two-time uh, scale. Now the first time scale is the traveling time through the preheating zone, which means how long the droplet will move from the edge of preheating zone to the premix frame. Then this traveling time is very important to be compared. how much time of this droplet to be complete evaporation. Okay, then this is the droplet evaporation time for the droplet. Okay, now in Whelan's book, they simply give you some estimation and to compare these two time scale. The first one, time scale, the traveling time through the preheating zone can be determined by the preheating thickness, the length divided by the speed, right? Because the flow coming from the upstream side, they are moving with the constant velocity. That means as you remember from the previous learning on premise frames, if you go away from the preheating zone, actually the frame speed is almost the same from the upstream side. We assume the velocity did not change too much. Then you can use your frame speed to be compared with the length. But this is the length you need to travel in. You need to travel, and the speed of your flow is SL. You divide it, then you will have a traveling time through the preheating zone. Now you can estimate by using the definition from the for the preheating zone from the premise frame studies. Then you can have this relation. Okay, the second time, that means that we consider the evaporation time for a droplet. Actually, you can go to the D square law. D square law will give you the droplet lifetime, right? Vaporization time is the lifetime of the droplet. Okay, and the TV can be estimated by this K is the evaporation constant by applying the formula for evaporation constant. Then you can have a relation to describe the vaporization time. Then you look at these two times, then you can identify, can we have a heterogeneous burning? The definition is if the evaporation time larger than the traveling time. That means that when the droplet passing through the preheating zone, because they need to have a longer evaporation time, then they will have a droplet burning or evaporation in the back premise frame, right? But for the TV, the vaporization time is more than the turbulent time. That means that all the gasification process will stop just ahead of the premise frame front. Okay, then the criterion is simply state that if TV small or equal to TR, then you will assume there is only homogeneous burning occurs, because droplet will complete their evaporation before the premise frame front. Okay, and put these two equations together, and the threshold for homogeneous burning, the threshold for the droplet radius for homogeneous burning will be described by this formula, and you can estimate for the regular hydrocarbon droplets. Then you will find out the initial droplets small or equal to 20 micron is a reasonable threshold for the homogeneous burning of these two-phase mixtures, and use this formula simplify our results to estimate if droplet size is small enough, small than the 20 micron, then you will assume the back burnings only have a gaseous burning without any droplet exists in the premise frame region, the chemical reaction region. Okay, and the loss estimation is reasonable, agree with the corresponding experimental observation of about 10 micron. Okay, from the experiment that we experienced the droplet droplet size more than 10 micron, then you always have a complete gasification of a liquid droplet before the premise frame. Okay, and this is the good estimation on those kinds of distinguishment between the homogeneous and the heterogeneous burning. Okay, remember, I emphasize again, what is the meaning of homogeneous burning? Homogeneous burning means the burning in the reaction zone, actually, they just only one phase. Okay, One phase means in the reaction zone, you may have a gaseous oxygen, gaseous fuel, and a gaseous products, but all the species are gaseous species. Okay, but for the heterogeneous burning means in the combustion zone in the flow field, they still have some liquid phase exists. For example, the droplet burning in the back gas phase reaction zone, or droplet evaporation. In both cases, they tell you in the burning zone, in the combustion field, there is a two phase exists simultaneously. Then we call this the so-called heterogeneous burning. Okay, and actually they try to estimate the flame speed for heterogeneous burning, and to be compared with the flame speed for homogeneous burning, we already described in the section of premise burning. Okay, and then you can figure out there is the dependence on droplets number and also the droplet radius here, and not and radius not. That this N naught represent the number of your droplet you may have from the beginning. The subscript not represent the initial condition N naught. Okay, this is the initial droplet number, and an R naught represent the average radius for droplets from the beginning. Okay. Now, from these equations, we can further to discuss by thinking about, because from the beginning for this two-phase flow, we already control the total liquid amount are the same, right? It's a fixed overall fuel oxidation ratio. That means the amount of fuel is fixed. That means the number times the volume of your droplets will be fixed. This represents the total mass of liquid fixed from the beginning. If this is a constant, that means then N naught times R naught will equal to, if this is a constant, then this will equal to 1 divided by R naught square, right? Okay, and you will find out this can be replaced by 1 divided by R naught square. Okay, R naught square can be have a square root. Then you will figure out from the bracket that will give you the relation between the flame speed with R naught by the inverse proportion. Okay, that means the flame speed is inverse proportion to the radius of your droplet from the beginning. This is very interesting to know that since the relation for the flame speed for the heterogeneous burning is inverse proportion to the initial radius, which means if you have a larger value of the droplet size, larger droplet, then the burning intensity will be small. Okay, it's a small. But when you decrease, your radius, that means that you think about the liquid droplet as small as possible, you will find out the flame speed may have a possibility to be increased to be higher than that for homogeneous burning. And this need to be justified for the further formulation, because this relation do not give you the limit for the flame speed for heterogeneous burning. Think about it. I just explained the flame speed is inverse proportion to the radius or initial radius of droplet, right? But this relationship tell you if you reduce the initial droplet radius as small as possible, then your flame speed may go to infinity. This relation do not give you the exact relation. They just approximately estimate. They have this kinds of behavior. The justification need to be solved or need to be analyzed based on a detailed study on it. And this basically those kinds of idea and a detailed study was proposed by my master thesis, and those asymptotic analysis was published by myself and Professor Low, my advisor, in 1988. We tried to look at the structures like that. We consider two kinds of burning. the lowest one, for example, for this figure, they tell the complete pre-vaporized burning. Actually, this mechanism represents all the droplets will be complete evaporation before they go to the premise flame. Here you can see from the upstream side, there is a two-phase flow, as we described earlier. There is some gaseous oxygen and a fuel vapor, and also a certain amount of droplets. Okay, and they may start to have a pre-vaporization at the x equals x3 because the temperature reached to the boiling point for the droplet. Okay, and they may finish the pre-vaporization before they reach to the premise flame, then which means xe here at this point, all the droplet finish gasification droplet disappear. Actually, in this region, the fuel and the oxygen are purely gas phase, and you will find out actually this premise flame is can be described based on the gaseous premise flame we already discussed in very earlier. But for the so-called partial pre-vaporizing burning, that means that they start to have a evaporation at x equal to xv, very similar to the previous case for complete pre-vaporized burning. But the droplet cannot finish the evaporation in the preheating zone of a premise flame. Then you may have a droplet exist in the downstream. In the downstream, then you will have several possibility to describe different kinds of droplet behavior. For example, for the lean spray, actually I put this L means the lean spray, you may have some oxygen left, right? You will have some oxygen there, and then the droplets still exist in the oxygen environment, they will have a burning. But for rich spray, R means rich sprays, you do not have oxygen because all the oxygen consumed completely at the premise flame. Then you do not have oxygen exist in the downstream side. The droplet, they can evaporate, but they do not have a chance to burn. Okay, but there is some complicated definitions for the criterions on the comparison between the stoichiometry on the liquid droplet and water. I don't want to describe it detail because those situations are described here. For many cases, you need to do a complete calculation, then you can have a result. But I don't want to explain this for more detail. You will confuse it, but I will show you the results. Okay, now we shift to the, let me change to the, okay, I think this we change the direction of the slides, then we can talk, have some discussion on the results. Okay, here, this is a result for calculation. We consider the three different kinds of spray. White T means the total equivalent ratio is around 1.15, and the other one is a 2, and another one, the third one is the 0.8. 0.8 means a lean spray. Overall is a lean spray. Lean spray means we consider the liquid droplet and also the fuel vapor come together, because some fuel will evaporate and becomes a certain amount of vapor, and we count the total fuel compared with the oxygen exists in this two-phase flow. Then totally is the link condition described by phi t equal to 0.8. Okay, and the phi t equal to 2 represent the rich conditions. Okay, and 1.15 for equivalent ratio represent the condition is very close to the stoichiometric ratio, and this one will give you a very some surprise results. Okay, now let's look at the lean and the rich case. You can figure out how it how the flame speed vary with your droplet size. Okay, let's look at the rich conditions. Actually, you can figure out omega represents represent the percentage of the liquid fuel you have. Okay, for example, 0.15, that means that you have a 50% fuel being liquid and 85% being the fuel vapor. Okay, and now you can see for given liquid ratios, you can find out if droplet radius increase, then the flame speed increase. This is simply to tell you because for rich conditions, means you already have enough fuel vapor for burning in the reaction zones. The extra liquid droplets actually they will evaporate, but those fuel vapor do not have a good contribution for the burning because they just give you the extra fuel vapor. Okay, and in the process, the droplet evaporation they need to absorb certain heat, which means for the liquid droplets in rich spreads, they do not have a good contribution for combustion, but they will absorb heat, make some heat loss to the liquid droplet for evaporation. That means that if you increase the droplet size as much as possible, then you will reduce the heat loss to your gas flame. Then the burning velocity will increase. Okay, you can see as you increase the liquid phase, okay, you try to, for example, if you have a small liquid phase, a small liquid droplet, then it is easier to be gasified completely. That means that they will absorb all the heat for gasification. And this amount of heat is large compared with the heat loss to the large liquid because liquid will evaporate longer to a farther distance, a farther downstream. They do not have a strong influence to the upstream premise frame. Okay. And basically, they tell you for the rich premixtures, rich spreads, if you try to reduce the droplet size and the amount of liquids, you will have a good flame speed. Okay. And for the lean case, they will give you the opposite effect because originally the spray is lean. That means that in the gas phase, you have a more leaner. The burning is weak, but the additional evaporation of the liquid fuel will support additional fuel vapor to burn, which means that you hope the liquid droplet will have some promotion to increase the fuel vapor coming out from the gasification process. That means that for the case of for the lean sprays, if you have a larger droplet size, okay, and or larger liquid fields, then the burning velocity will be decreased because large droplet size will prevent the fast gasification to provide large amount of gaseous fuel. Then if they cannot support the burning become stronger, then they have a weaker less flame temperature here, the flame speed here. And then you look at the stoichiometric case, surprisingly, you will find out when you increase the liquid loading, the percentage of liquid fuel, you will find out in the there is the region when you look at the droplet radius larger than approximately 20 or 15, then in this region actually you have a so-called heterogeneous burning. But near the droplet size, small droplet size region here, you may have a homogeneous burning coupling with the droplet burning in the downstream side or evaporation. I will not describe it too detailed, but they tell you there is a possibility to have a higher burning intensity, in this case, even higher than the premise burning. Okay. This is quite complicated to explain it, but you just know there is some influence coming from liquid loading and the droplet radius. If you are interested in this detail explanation, you can go to our paper published in 1988. Okay. But anyway, I give you the final comparison, let you know the importance of the results. Okay. The left-hand side tell you, okay, here for the small droplets, if you consider the small droplet, the spray with a small droplet, here the droplet radius is around 20 micron, and the right hand side is the 50 micron, is the larger the spray with a larger droplet radius. Okay, and you can see the French speed distribution. The homogeneous limit represents this is the flame velocity corresponding to the gaseous premise flame. Okay, now they tell you if you increase the liquid loading, that means that you have a more liquid droplets from the point from the 4%, 8%, 12%, and 60%. You can see the flame speed curve will shift to the rich side, and the maximum flame speed is increased continuously. Okay, and here you can see if you look at for a given total stoichiometry ratios, the liquid loading increased, then the flame speed increased too. But for the rich one, for the rich spread, actually the flame the flame curve, flame speed curve shift to the rich side is very similar to the shifting of the flame curve, the flame speed curve as shown in the left hand side. But the maximum flame speed basically they are decreased. Okay, they are decreased. But in general, when you have a certain amount of liquids exist in these two-phase mixtures, the whole flame speed curve will shift to the rich side. Okay, and these results can be justified by experiments. Okay, let's bring the other the next page to show you. I need to make change. Need to change the orientation of the. Oh no, I'm sorry. I need to use the other slides. Okay, yeah, we do have a comparison here. Okay, let's see. We look at the paper Hayashi, Kumaga, and Saka in 1976. They did a very nice experiment how to do that. There is the so-called epsilon. Epsilon is the expansion ratio. They did the experiment by this. There is the combustion chamber, and there has some piston moving. Try to have some expansion of the volume of your spray. When you do the large expansions, then you will reduce the pressure inside of your combustion chamber. Initially, you have certain fuel vapor inside of the control of the combustion chamber. When you expand it, that means the pressure reduce. When the pressure, overall pressure reduce, they will let the fuel vapor has a chance to be condensed. Okay, since the total pressure reduced, they will go to the lower pressure, then they will condense to the liquid phase and very uniformly distribute. And when they condense, that means they will nucleate the small droplet, right? Okay. Now here they tell you they do the different kinds of expansion ratio by suddenly expansions. The expansion ratio is 1.55, 1.36, 1.18, and it has larger expansions. That means that you will produce the more uniform, larger droplets exist in this combustion chamber. Okay, then they ignite it and they try to measure the propagation speed of a spherical flame. Okay, and then they find out the interesting thing is here, lambda is the overall equilibrium ratio. Okay, or they use the fuel ratio. You can imagine this is equivalent to the equilibrium ratio. You can think about that. And the vertical axis represent the flame speed. Okay, and the interesting thing is, okay, and you have a large expansions here. There is the solid circle line show here. This is a flame speed curve, and then the square, open square, okay, and then the triangle, and the open circle represent the premix gas. Premix gas in the inside the combustion chamber, they do not have a liquid exist. Okay, and this result is perfect. be compared with our theoretical prediction. They tell you if you increase the amount of liquid fuel from the 1.18 to 1.636, 1.55 by expansion ratio, that means that you increase the liquid fuel loading, the French speed curve shift to the right side. Okay, and you can see the maximum frame speed actually reduced a little bit, okay, but they are higher than the maximum frame speed for the previous frame. And it seem look at the whole structures is that all the frame speed variation with the liquid fuel loading are quite similar to that predicted by the theory, asymptotic theory. Okay, and up to now, actually, we try to emphasize there is a modeling on spread premise burnings, but actually, those kinds of behavior that tell us the back burning get involved with the heterogeneous burning and also homogeneous burning. And those kinds of burning structure basically is not easy to be described, but they tell you there is some optimal burning situation based on the droplet radius and also the amount of liquid loading you may have. Okay, and you try to link those kinds of evaporation from evaporation process for the liquid droplets, and I try to think about how much fuel vapor can be contribute to the overall back burning. Those kinds of balance will give you the some idea to optimize the burning intensity. Okay, but it is very hard to explain in detail for the spread premise friends. But I just give you try to give you the idea actually for the spread burning, the interaction between the liquid phase and the gaseous phase are quite important, and contribution coming from the droplets is an important part, and it depends on how much droplets, the size of the droplet size, and also the amount of the liquid loading. Okay, the fuel loading.